Right, hello. This is feedback on the depth paper that you did last Thursday. So here we go. First question. I think I've already mentioned this in class. You must know the apparatus, different types of apparatus. So if you're making up an accurate solution to 250 centimeters cubic, it will be volumetric flask. If you're measuring something like 25 cubic centimeter portion, it will be a pipette, and so on. But you need to know that apparatus. And if you're not sure, talk to me about it and I'll show them to you again and remind you what they look like and tell you what we use them for. Okay, then we're told that this acid A, reacts with NaOH in a 1-to-1 ratio. So that's pretty straightforward to calculate the molar mass of A. So here's our equation we're going to be using. Work out how many moles of NaOH we have. That will be the same number of moles of acid A, but remember that's only in 25 cubic centimeters, and we're making our acid up to 250 cubic centimeters, so we need to multiply that value by 10. So that's how many moles, 3.03 times 10 to the minus 2 moles in 250 cubic centimeters. And then we just work out molar mass, mass over number of moles. Mass is given to us in the equation, and there we are. Okay, with a titration, you very rarely would you just do one titration. To get a titer, you would need to confirm your results. So you're going to repeat your titration until you've got at least 2 titrations that are concordant. Okay. So they should be within 0.1 cubic centimeters of each other. And then you take the mean from the concordant titers to iron out errors. Okay, sigma bonds. This is you're given a molecule here. You're asked how a sigma bond forms, because an alkene has sigma bonds and pi bonds. Don't get confused with the pi bonds. The sigma bond is between the bonding atoms, or between the nuclei of the bonding atoms. That's the crucial thing. And don't talk about S or P orbitals, because it depends on the molecule. So just say overlapping orbitals between the nuclei of the bonding atoms, or just between the bonding atoms. Bond angle around the double bond here is planar. This is a planar part of the molecule. And it's trigonal planar because there are 3 bonds effectively. Don't forget that the double bond is treated as a single bond in this case. So trigonal planar, 120 degrees. And you're asked for a mechanism, electrophilic addition mechanism here, bromine adding to the alkene. And to get all the marks for this, it's pretty easy if you know what you're doing. As long as you've got your dipole on your molecule here, you've got your curly arrows accurately placed, yeah? So this curly arrow is coming down towards the bromine. This curly arrow is going from the bond, it's quite specifically from the bond to the second bromine. Then we've ended up with our bromide ion. So I would always put a lone pair on it, because you can show that the curly arrow is coming from the lone pair to the full positive charge that is on the carbocation, and then your product. Okay, 4 easy marks really. Curly arrow, what does it represent? It represents the movement of a pair of electrons, not just of electrons. Okay. Well, the double-headed curly arrow, that is, but we don't use the single-headed one. So, okay. So we're told pentwanine has a molecular formula, but it does not show stereoisomerism, and you're asked to explain why. Crucial thing about stereoisomers is they have the carbon in the double bond, both carbons that are attached to the double bond have to have different groups attached to them. Now because the double bond is at the end of the molecule, this carbon here has got 2 hydrogens, so it cannot exhibit stereoisomerism. Okay, so here we're asked for to show the cis trans isomers of pentwanine. So whenever I'm drawing these, I would draw my double bond first and do like the bow tie arrangement, and then put the other bits on. So as we can see, these two carbons have got different groups on them. This carbon on the left has got a CH3 and an H, and this carbon on the right has got a CH2, CH3 and an H. That's the difference between forming stereoisomer or not. And then the cis-trans cis, remember you've got the hydrogens on the same side, cis for sisters, and then trans hydrogens on opposite sides. This one, not so straightforward because we have to use the Kern-Ingold-Prelog rules to identify which are on the same side and which are not. So we're looking for two ones either on the same side or on opposite sides of the double bond. But first of all, we have to assign them as 1 and 2. So we look at this carbon here, and we look at what is joined to it, and we look at the atomic mass of those two elements. So we've got fluorine and carbon. So fluorine has a higher atomic mass than carbon, so that is assigned number 1. On this side, we've got 2 carbons attached to the carbon, so we can't use that atom. We need to move along the substituent as such and find a difference. So here we can see that there is an oxygen and there isn't here. So this one would be assigned 1 because oxygen has a higher priority than carbon. You could add up the two the masses of the two groups there, and again CH2OH would be assigned 1 because it would have the higher mass. Okay, so then we just look to see, are they on the same side or on opposite sides? In this case they are on opposite sides, which means E isomer, the E isomer, E for enemy, okay, or Z on Zane side. Ha ha ha. Okay, number 3, graph here showing us boiling points and relative molecular mass of molecules. So this is definitely going to be about bonds or intermolecular bonds, okay. In this particular case, because these are all molecules, it's going to be about intermolecular bonds or forces. You're asked to explain why H2S has a lower boiling point than H2O and H2SE. Okay, so the easiest way to do this is to break it into the 2 parts. Look at H2O and compare it to that, and then look at H2SE and compare it to that. And then you're actually covering the whole question. So I've explained here that H2O has hydrogen bonding between the molecules, but H2S only has London forces. And then again, that same statement that you pretty much always have to use. Hydrogen bonding is stronger, requires more energy to break, therefore H2O has a higher boiling point. And then the comparison with H2SE. So H2SE and H2S both have London forces acting, yeah, but H2SE has more electrons, stronger instantaneous dipole stroke induced dipole, therefore requires more energy. And there's your 4 points basically. You're asked to estimate from the graph the relative molecular mass of, the boiling point of H2PO. So you just go back up to your graph obviously and extrapolate it a bit, but not, you've got to go along to the relative molecular mass, which is 211. So somewhere about here, isn't it? Yeah. Okay, some of you went much too high. In general, most of you got that right. And then again, we're doing another comparison here. SO2 and MgO both contain oxygen. Yeah, so what? Shows the melting points. Predict the type of structure and bonding. Predict the type of structure and bonding of SO2 and MgO and explain the difference in their melting point. So we have simple molecular lattice with covalent bonds, yeah, between atoms, and intermolecular forces between the molecules. So that's explaining the structure and the bonding of SO2. And then MgO is a giant ionic lattice, that's the structure, with ionic bonds between the oppositely charged ions. So we've done structure and bonding, and now we've got to explain the difference in their melting points. Ionic bonds are much stronger than intermolecular forces, therefore take a lot more energy to break. It's as simple as that. Break it down. Okay, question 4 rather, looking at group 2 metals and how they react with water. So you're asked to write an equation and include state symbols, which I have done on this side but not this side, which is a bit naughty. So this one is aqueous and this one is obviously gaseous. Yeah, solid, liquid, aqueous, gaseous. Solid, you should know that because it's a metal, and this is obviously because you've got OH minus, and it's going to be in water. Okay, right, because it's reacted with water. Yeah. Then calculate the concentration in moles per dm cubed of strontium ions in the resulting solution. So we have to look and see what information we've got up here. We've got 0.2 grams of strontium, so we divide that by the atomic mass of strontium, which tells us the number of moles, and then we're asked to calculate the concentration in 250 cubic centimeters. Yeah, so concentration is number of moles divided by the volume. Don't forget, obviously 250 divided by 1,000. Or you could do up here multiplied by 250 over 1,000. Yeah. Hang on, no, ignore what I'm saying. Okay, that's how I would do it, but there is another way of doing it which works just as well. Depends how confident you are with your maths. Okay, so concentration of strontium ions, there we are, 9.13 times 10 to the minus 3 moles per dm cubed. Okay, and then you're asked to compare calcium and strontium, both group 2 metals. Predict a difference in the volume of gas produced by calcium and strontium. Explain your reasoning and include a calculation in your answer. You're not really predicting if you're using a calculation, but there we are. That's the way the question's worded. So we work out our number of moles of calcium that we would have. We already know the moles of strontium that we would have. So we've got more moles of calcium, which would indicate that there will be a larger volume of gas, and we can show that by calculating the volume of gas for each. Okay, ionization energy, write an equation, include state symbols, so don't forget that it's always in the gaseous state. Okay, we're starting with an atom here because it's the first ionization energy, and then we've got a positive and electron. Looking at successive ionization energies, and you're asked to identify which group we're looking at with a justification. Okay, looking at the data. So I just did a quick calculation. That 1145 minus 590 gave us that difference. 4912 minus that gave us that difference. So there's a big jump between here, first and second, and then the second and the third, which would indicate that we're in group 2. Because we've lost the outer 2 electrons and we've moved in now to the next shell. Question 5. Why does this equation represent the standard enthalpy change of combustion of butane? So obviously if you don't know the definition of the standard enthalpy change of combustion, which is 1 mole of a substance completely combusted, it's very difficult to get that right. So you've got 1 mole of your butane there, and it's completely combusted in oxygen. Complete combustion because we've got CO2 and water. Yeah. What's the potential danger of incomplete combustion? It's the production of CO, carbon monoxide, which is toxic. And then you're asked to have a look to see whether or not a heater would be safe burning in a room where it consumes a certain amount of oxygen. Okay, so you need to work out how many moles of butane you've got here. Yeah. If we look at the equation, our ratio is 1 to 6.5, so we need at least 6.5 times many moles of oxygen to completely combust our butane. Yeah, so number of moles required, 67.21 moles. So then if you work out how many moles that is, 1.5. Now notice this is 1.5 cubic meters of oxygen. So this equation this equation, you need to have cubic decimeters, so you need to convert your meters to decimeters, yeah, and then divide by 24, and that tells you how many moles of oxygen were actually used. So then when we compare the two, we can see that we haven't got enough oxygen here. We need that much, and we've only managed to burn 62.5. So therefore your heater is not safe. You've got incomplete combustion because 62.5 moles is less than 67.2. Right, okay, and then we're asked about an alkane X, which is also used as a fuel, and we're told that on complete combustion of X, we produce 2 × 10⁻³ cubic meters of carbon dioxide gas, okay, measured at a certain temperature and pressure. So that's a hint that you're going to have to use the ideal gas equation when they put that kind of information in the question. So quickly scribble out your ideal gas equation and then look at what you're trying to calculate. So you're being asked to determine the molecular formula of X, okay. So we need to know the number of moles. So we need to rearrange the equation for number of moles. Then it's very important with this equation that you remember to convert units. Check the units you're given in the question and make sure you've converted them properly. So we're told 101 kilopascals has to be in pascals. 2 × 10⁻³ cubic meters, that's fine. Cubic meters is fine. The gas constant is you're given that, I believe, on the data sheet. And then 24 degrees C, we need to convert to K. And then you just do the calculation, yeah? So we can work out how many moles of X we've got. Now, we know that if it's complete combustion, that the ratio of CO2 to the carbon in your alkane will be 1:1. So we've got the moles of X, and we've now got the number of moles of X, and then we're told that complete combustion of that many moles of X produces this much carbon dioxide. So if we divide that value into that value, because of the ratio of 1:1, that will tell us how many carbon atoms there are. And as it's an alkane, then we know that it must be H16 using the formula for alkanes, yeah, general formula. Okay, part D, this is Hess's law or Hess cycle question. Important to recognise that you are being given combustion data, which means that you must have your combustion products at the bottom and your arrows go down towards them. Okay, and we're trying to find out this over this arrow here. It's pretty straightforward. If you've drawn your cycle correctly, you can work out your two roots. So it's this plus this. X plus that equals that. Okay, there we are. And then you just do the calculation. Try and remember to put the positive sign in, please. Okay, you may get away without it, but be on the safe side, always put it in. Question on equilibrium. Okay, and it's a starred question, which means they want a nice coherent answer to get your 6 marks. All right, so first of all, you've got to explain the conditions of temperature and pressure that could be used to obtain the maximum equilibrium yield. Okay, and then you have to discuss the importance of a compromise. There's 2 parts to the question. So first of all, look at temperature. Yeah, so, exothermic reaction. If we reduce the temperature, we will increase the yield. However, yeah, it will reduce the rate. Then look at pressure. If we increase the pressure, we are going to push the equilibrium over to the right because there are less moles there. You need to state why. You know, here you've got to state that it's exothermic in the forward direction, and that's why if you reduce the temperature. And here you've got to state why you would increase the pressure. I don't think anybody picked up on the fact though that if you increase pressure, you will also increase the rate. Yeah. So nobody mentioned that. You all talked about the safety aspects of it, but they're not really asking about that. They're saying explain the conditions that could be used to obtain the maximum equilibrium yield. So they've not asked about any limitations of pressure or anything. So you will increase the rate if you increase the pressure. So that should have been mentioned. And then finally, the compromise effectively will involve temperature, because pressure's fine. Yeah. So that increasing the temperature will decrease the yield to an acceptable level, but will produce SO2, SO3 in a shorter time. Hang on a minute, I think I've got that the wrong way around. I've said the compromise involves temperature, so that increasing the temperature will decrease the yield to an acceptable, but will produce SO3 in a longer time. Sorry, ignore that, shorter time. Make sure that you make note of that, because it takes longer to produce it. Okay, rate of reaction question. You're given again an equilibrium. You're given some concentrations and over time, and asked to plot a graph from the data. So you've got the graph the wrong way round. Time pretty much always goes on the x-axis and your concentration on the y-axis. Okay, you need to use the whole of the graph paper. You make your graph as big as you can. Okay, I've used Biro here, but really you should use pencil. It should be a sharp pencil. I've said this to you many times. Big thick lines scrawled across a graph paper are not acceptable. Okay, because how can you read accurately a value when your line is so thick it takes up 2 squares? Okay, so you got your 3 marks for labeling the axes, drawing the graph using up the full graph paper, okay, and plotting the points correctly. So 3 marks for that. And then you had to use your graph to work out the initial rate of reaction. Now remember, you need to draw a tangent that goes through the origin and follows basically that initial part of the curve. Then you draw your right angle triangle and you take the difference in y over difference in x. So obviously where your top of your triangle, so because it's 0, it's nice and easy. 0.04, what did I say, 0.043 coming across here, and 80 seconds across the bottom. Okay, do the calculation and there's the answer. But don't forget how to work out initial rate. And initial rate is you have to draw a tangent. So if you hadn't got the tangent on the graph there, you couldn't get the mark for it. Then you're asked to draw another line that would show the production, or the concentration, the rate, sorry, using, if you added a catalyst. It's obviously going to be faster at the start, but you're not going to end up making any more SO3, are you? You're going to get the same amount. It's just you've added the catalyst, which is not involved in the reaction, but makes it happen faster, that's all. Okay, definition of catalyst here. You're told it's a solid catalyst. The reaction is a gaseous state, so it's obviously heterogeneous. You need to know those definitions. Why are catalysts beneficial to the environment? There are a few reasons. The most obvious one is that it lowers the energy demand. The other thing you could say is that you're going to use less fossil fuels because it lowers the, which reduces global warming. There's also the atom economy aspect of it. Maybe the alternative route has a better atom economy. So there's a few things you could say, but that's probably the most obvious one. Then your Boltzmann distribution, you need to be clear on how to draw a Boltzmann distribution, and this is how you draw it. You must have the start of it, must be at the origin here, and it must be within that first square, quite clearly. Go up. Now this is a catalyst, representing the addition of a catalyst. Boltzmann, so there's only one curve, up, down. We don't want it finishing up here somewhere, okay? But it must not meet the x-axis. So round about that bottom square is fine to finish your curve. And that's your activation energy originally, and that's your activation energy with the catalyst added, which gives an indication that number of molecules is increased when a catalyst is added. You need to know the labels on those axes, okay? And then your explanation that we've got an alternative route with a lower activation energy, and which means that more molecules have the energy above the activation energy, so you get a faster rate. 4 marks, quite straightforward if you can draw that graph. Even if you don't explain it properly, you get 3 marks. And then this is the final question, which is another starred question, and I've set up here, you need to plan this before you write it. Scribble down a plan on the back of the exam paper or something, so that you don't start getting muddled up with what you've written, you know, and the order that you've written it. Very important that you follow the instructions, okay? Read this carefully. So we've clearly got here 3 different alcohols, a primary, secondary and a tertiary. You have access to normal laboratory apparatus and chemicals, quick fit apparatus and an infrared spectrometer. Describe a plan that would allow you to identify the 3 alcohols using the same experimental setup and method. So you would only do one process, follow through one process, okay? And it says you will also need to provide equations using structural formulae and a description of how you will identify the 3 alcohols from observations and results. So the first thing to say is that we've got those 3 different types of alcohol. Secondly, if you reflux all of them with H, we need to put this in, the conditions, H plus and Cr2O7 minus. If you reflux all 3 of them, then you'll straight away recognise the tertiary alcohol because there'll be no colour change, so that's easy. So then we're left with our primary and secondary alcohols, and we'll have to use our infrared spectrometer to identify the products of the refluxing. Yeah. You need to talk about the infrared spectrometer. They haven't told you it's available for nothing. So your primary alcohol obviously will fully oxidize because we've refluxed it to a carboxylic acid. So you can write the equation out for that. And also on our infrared spectrum, because it's a carboxylic acid, we'll have a very broad peak between these values showing the OH group, and a sharp peak between these values showing C double bond O. And whereas with the secondary alcohol, we would get oxidation to form a ketone. Again, you need to write the equation. And on the IR spectrum this time, though, there will be no broad peak showing the OH. There will only be the sharp peak showing the C double bond O. So pretty straightforward, actually, to get 6 marks on that. That's quite a nice question, but I'm not sure that many of you did get 6 marks on it. Okay, that's it. I think that's the last video you ever got to watch from me. Okay, see you later. Bye.